Hello everybody! Welcome to the next in the series of our MPS screencasts. Here it is Václav Beck talking from Prague, and on the other side of the wire
is Markus talking from Stuttgart, Germany.
Hello, welcome.
Hello. So this is the first of 3 screencasts that rehash or re-explain some of the basics, right? Type system, generator, and editor definition in MPS, right?
Perfect. Yeah, I think that will be exciting.
Yeah, it's these are really 3 interesting aspects of the whole system, and so talking about that in some more detail is probably useful.
Yeah, I believe so, and they are also probably the most involved one, involved ones. If you really want to understand how MPS works, and if you want to benefit from what it provides.
Type system can be non-trivial, yeah. So let's start with the type system, right? And take a look at some example code, and then based on the example code, we can take a look how it works.
Yeah, good. But looking at the code, it doesn't look like Java.
No.
Tell me more.
Yeah, no, we're using C here. It's the C implementation of the embedder project, and the reason for that is twofold. One, the type system of C is much simpler than the type system of Java, so explaining some of the things is cleaner and not as complicated as in Java. And the other thing is that I have built most of the C implementation, so I know it much better than the Java type system, so I can talk much more, authoritatively about what we're doing here.
Mm-hmm.
But I mean, the way to describe the type system rules are the same in every language, so it doesn't matter what you use to explain it.
Right. So the rules that we'll show now, people can apply them to all or to any language that they decide to create in MPS, right? So
well,
the rules will be kind of, the principles remain the same.
Strictly speaking, the type system rules that we're going to see are, of course, C specific. But if you look at this local variable declaration in the first line, well, it looks the same way in Java, and it looks probably mostly the same way in any other language. So
right.
That can be directly reused. But also, the way how you define these rules is, of course, a built-in MPS capability, and explaining that capability, that's what the point is. And so that would be useful in any other system.
Great. Wow.
So I guess we can start with the first statement here, right? This is simply a local variable declaration. And you can see that we have declared it as an int 8, and we assign it the number 10. And of course, if we assign it 10.2, then we get an error that it doesn't work. So there is a type system rule that makes sure that the stuff in the init expression is compatible with the type itself. Okay?
Mm-hmm. Okay.
So let's do a couple of mechanics. You can always at any time select a program element and press Ctrl-Shift-T, and that gives you the type system info window, which basically tells you that the type of this guy here, the 10.2, is float. Okay.
Mm-hmm.
And if you do that on an int, the thing will probably be int. And if you do,
you were not sure.
And if you do that on the whole local variable declaration, it's also an int. So let's first take a look at why the local variable declaration's type is an int, right? I mean, it's not necessarily obvious. I mean, the type of int is int, but the type of the whole local variable declaration, that's also int. So how does that work?
Mm-hmm. Okay.
So let's go to the definition of the concept with Ctrl-Shift-S, and then in the tabs here you can see there is a type of specification, and we can select that. And it says, for example, that the type of the local variable declaration's init expression, so that would be that guy, must be the same or a subtype of the type property, that guy, of the local variable declaration.
Now, okay, looking at this, sorry, I'm a bit slow in here. So, looking at the type rule, now the LVD thing, that's the structure representing the local variable declaration, and it has a child element in it.
Yeah. If you go to the definition, it has a child called init,
which is an expression.
Which is an expression, and as you can see, it implements the iTyped interface, and that guy has a type.
Yeah. All right. So there's where type comes from.
Yes.
Okay, and we refer to these guys in the type rule.
Yes. And basically this rule establishes the compatibility between the init expression and the type itself, but it does not calculate the type of the whole thing, right? And the reason why we don't have to do that here is because local array declaration extends or implements the iTyped interface, and it has a typing rule which says that the type of the whole thing is the same as the type of its declared type. Right?
All right. Well, wait a minute, please. Looking at this rule here, the rule we've seen before. Okay, so the type rule here and the type rule of that we created in local variable declaration.
Of that guy.
I noticed there's a difference in them. You know, one of them says check and the other ones doesn't. You know, I think it's important to mention the difference.
Absolutely. So the case where it does not say check means that there is type inference or type calculation going on. So the type of that guy is transferred to be the same as this one. So it assigns this type. Now in that case, we don't do that. We have set the check only property in the inspector to true, and that means that there is no type inference going on, but rather only there is a check performed, so that if this is not correct, then you get the error, which is the case here. Right?
Okay, good.
So, by the way, a very important feature which is not documented much, but very useful. You can see that there is an error. Whenever there is something underlined in red, you can do Control-Alt-Click, and you get this dialog which has a Go to Rule button, and that then shows you the rule that resulted in the error that was underlined. That's a very useful debugging tool.
Which rule is it in our case? Oh, that's the...
It's the one that establishes the compatibility between the init expression and the type.
Okay, good.
Okay, so let's fix that. So next line, we assign an integer to a float. Why does that work? We tried to assign a float to an integer, which did not work. Why is it possible to assign an int to a float? That is because if we go back to the definition of the rule, actually we can create more space here. We said that the type of the init expression must be the same or subtype, right? This operator here means that the side with a smaller sign is basically must be a subtype of of that guy all the same. And so how does that work? Well, there is a subtyping rule which determines that that int is a float. Int is a subtype of float. In other words, if you go here, it says there is supertype of float type, and it says it's double, and its supertype, well, it's a little bit involved in C, is long double. And then there is another one that says there is a so-called weak supertyping rule that says that the supertype of a floating point type is basically an integer type, so you can use an integer wherever a float is expected.
So this is a special type of type rules called subtyping rules.
Absolutely. There are several typing rules. We can look at that in the project. There are so-called normal type inference rules, right? If you try to create a new rule, there is an inference rule, which is the one we saw all the time, which just establishes relationships between types. And then there is subtyping rules, where you return the supertype of some type as a way of establishing a hierarchy of types. Note that this hierarchy of types is not necessarily the same as the inheritance hierarchy of the concepts that represent the types. Okay, so my language concept int type does not extend the language concept float type, or the other way around.
Sure.
Right? These are separate concepts, and then the logical typing inheritance or typing specialization relationship, that's what you do with these subtyping rules. As you can see, there are a bunch of other rules or kinds of rules, and we will see some of them later. Not all. Okay, so let's go back to the demo. Here is other interesting stuff going on. So we have an array. So let's first check what the type of that guy is, right?
Let's have a look.
That's not very helpful. It's
all right, it says the same thing.
Yeah, but the point is, if you look at the inspector, you can see it's an array type, right?
Right.
So if you go to an array type, an array type is a type which has a base type, in this case int, and an array size spec, right? That would be the 3. So this is how this is specified. Now, this is really interesting. We want to be able to specify a type, an array initialization expression. And the question is, what is the type of that guy? I mean, if you look at it, it's an array of int of the length 3, which is good because then it's compatible, right? If there were another one, then it were not compatible because the length doesn't work. So how does it calculate the type of something like that? Because, you know, the thing is, you could do something like this, right? What's the type of that? And of course, this is now is a problem because that needs to be the same here. But the point is, the type calculation of this thing is really interesting. So let's take a look.
It must be, yeah. I'm quite curious to see.
So type of array init expression. I'm going to move it over here. How do I do that? Move to opposite group. And I wanted to see the type. So let's see if we have enough space here. So that's a little bit more complicated.
Mm-hmm. But so, it still fits on a single screen, which is good.
Yeah, that is actually true for many complicated MPS things, because the languages are so dense or so domain specific that many interesting things fit on a page. Doesn't necessarily mean that it's easy to understand just because it fits on a page.
Right, but you save your hands from scrolling.
That's true.
No.
Okay, so I'm just gonna create some more space here. So what does it do? Well, first of all, we have to make sure that all the types of that thing, all the types of all the expressions, that they are all the same.
Yeah, that you only have integers inside that array that you're creating, right?
Or only floats or only strings.
Right, in our case, integers.
Yeah, right. So what do? That's extremely interesting. So we create a type system variable, base type. It's just a free variable. And then we iterate over all the expressions in this array init expression and claim that the type of each of these expressions must be the same or a subtype of this base type. So, you know, the MPS type system works by inference. So that means you as the programmer, you specify a bunch of typing equations, and then the system tries to solve them all so that the whole type system, all the equations you've specified, are all true and consistent. And so by declaring one variable here and then saying that all the types of all expressions must be the same or subtype of that variable, that means that MPS infers the type of that variable to be the common supertype of all the the expression types.
Mm-hmm. Okay. So it will add an equation for each iteration through the loop.
Yes.
And then it will solve them.
Yes.
And the only solution, obviously, is that base type must be a supertype of all the elements.
Same or supertype, exactly.
Right.
Yeah. Well, and then once we have, I mean, that's the key, right? That is the key.
Right.
And then what we do next is we just create an array type and we set the base type of the array type to be that guy. I mean, this is the same name. We should maybe call this inferred common type, right? I mean, just so it doesn't look like.
And here you do just assignment, no inference rule.
That is true, because we know that it's exactly the same object. We create a new one which can just assign it here.
Okay.
Yeah. So then we have to think about the size of the array, and in our case, it's not like an array has a size just as an integer. It may also be a reference to a constant, which is why we have to explicitly instantiate an int literal array size spec, and then we basically grab the size of the number. I mean, you know, we grab the number of expressions here by using size on the expers collection, and then we set the size of the array type to be just that guy, and then we claim that the type of the whole expression is basically the array type that we've created.
Okay.
So the key really is to understand this thing. The ability to just write down a variable and then iterate over stuff and assign it to the same. You know, if this were assignment, then it wouldn't make sense, because then you assign something else to the same variable, and its value would be the kind of last assignment. But this is not assignment. You establish a new equation for each iteration.
So basically, you're building these equations, and then at some point they will be all evaluated, and a solution will be found.
Yeah, hopefully. If not,
if not, then you get an error, right?
Yeah, and you know, in some sense, this finding a solution is a global process. It takes into account all equations that have been written in the whole, well, scope visibility, and sometimes this leads to the problem that the error is actually highlighted on the wrong node. For example, if we go back here, and if you say, you know, if you say something like that, instead of fixing, you could fix it by either changing that guy or by changing the type here. But intuitively, you think as a programmer that the type is probably correct and the initializer is wrong. So you want to make sure that MPS highlights the problem in the initializer and not on the type. Because from a typing equation perspective, both could be the problem source, right?
Oh yeah, that's right.
And so you do that. I'm not sure actually whether we did it here because it may just work by default, but you can specify that by saying, yeah, you see we say that, node to check. So that is the node that actually should be checked and on which the error is then underlined.
So here you say that if this is not valid, then this is the guy to blame.
Right, exactly, yeah, well said, yeah. Okay, so let's look further. Here is something relatively simple, right? Here we assign an array element to an integer, and of course, if that is an int array, then the the first element of that array must be an int again.
Sure.
So we can take a look at that typing rule. It's a bit annoying that it always opens it in the wrong thing here. So that is also interesting.
Yeah, hey, that's even more involved than before.
Well, yeah, and I have to admit I copied that from base language, and I don't completely 100% understand it. So
all right,
basically,
let's try to figure out together.
Yeah. So the thing is, basically, what you want to say is that the type of the thing here, of the whole array access expression, is the base type of the array that is on the left side, you know, of that guy. Right?
No, so all right. Well,
so let's look at the structure. An array access expression has two children. An expression for the index, that would be the 0 here, and inherited from unary expression, the context expression, that would be an array. Okay?
Yeah.
So that's the structure. Just so we know about the structure. Now, where did it go?
The type rule is gone.
Yeah, well, the selection is sometimes a bit unintuitive, you know, whatever. So first we create one of these variables again.
Right, so this is a type rule that tells you each time you put square brackets after an array with index, you know, what is the type of this thing.
Yeah, yeah.
Good. Yeah, just
so
to make sure.
The naive way of writing it would be simply to say the type of the array access expression is the same type as
the
array.
elements.
Yeah, you take the expression itself and you ask it for its type.
Right.
So that would be type of AAE dot expression. You know that this is an array type, and you ask it for its base type.
Yeah, so you cast it to array type, ask for the base type, and that should be integer. So right, well, the naive approach seems to be, you know, valid.
Yeah, and so that's how we had it, and that worked for one-dimensional arrays. But if we have multi-dimensional arrays where you can write, you know, where you can put another one of these square brackets here, so it would be the first element of the first inner array, if you put 0, 0, then it didn't work anymore. And I actually don't understand exactly why, but now this way you do it so differently. You create a variable here. You then say that somehow the type of the base context expression of the array thing must be that, so you kind of extract the type of the expression itself.
Okay, and you store it in T in the
and
variable.
then you say and then you associate that with the array access expression, and and that's it. So I can't explain. See, the point is that here it says this is an array of that type. You say that the array access expression's expression, right, that guy, must be an array. You see the brackets here of the T thing. And then, so that kind of extracts the t. And then you say that the type of the array access expression itself is t.
Yeah, well, that makes sense. Now I'm wondering, why do we use, anti-quotation, right? That's the percentage mark we have.
Yes.
We didn't use it in the type rule we were looking at before. But we were using variable as well, but without this. So this is kind of puzzling. But it probably it's probably important to have it done this way. Just don't know exactly why.
Exactly, that's the point. But it works this way.
Good.
So that's why I said, that the type system is really because it's declarative, right? It's not a procedural piece of code. It's declarative, and there is this sophisticated algorithm going on. So it's not always easy to understand. And then this last line, that's obviously simple. It just says that the index must be int 64 or a subtype of it.
Sure.
Right? So that's easy. So actually the interesting part is that guy here.
Yeah, basically it's kind of, you split the naive approach into two lines, if you say, right? It's a kind of you split that the single line we had into two lines with this variable. Okay.
And for some reason it works for multidimensional arrays. So that's the thing. Whereas the other solution does not.
Okay.
Okay, so next case we have an addition here where we have the plus operator, right? The plus operator is simply move to object group. The plus expression is a binary arithmetic expression, which is a binary expression which has a left and a right argument. So an int would be the left argument, another int would be the right argument. Now, here, typing works differently. There is a different technology or a different set of rules is used, and that is the so-called overloaded operation containers.
Yeah, okay, right.
So let's take a look at the typing rule of binary expression. There is.
I think we've seen something of that sort when doing the the screencast on money, when we were adding money together.
Yes, because in that money case we had to override that thing. Right? So basically what it does is it waits until the left type is calculated. So this when concrete expression is basically a way of saying that this type calculation should only be tried if or when at the time when the left type and the right type have already been calculated, because of course the resulting type of a plus expression depends on the left and right argument. And so these have to be calculated first in terms of types.
So is it sort of a way to delay this rule until these guys are concrete?
So basically these type system things, you specify a bunch of equations and MPS tries to solve them. And this is basically a hint that says don't even try that until the type of left and right have been calculated.
Wow. I wonder what would happen if we omitted when concrete.
I can tell you it doesn't work.
It doesn't work. It would it would run the equations too early.
Yeah, at least in some cases. I mean, because I think it's basically non-deterministic, right? And I mean, obviously there must be some mechanism in MPS that orders these things, because there are many places where the ordering is kind of important. But in some cases it simply doesn't work, and then it usually can be fixed by putting a when concrete around it. And that's what we did here.
I see. Right. Perfect. That's a good heuristic, right?
Yeah, if it doesn't work, fix it.
Fix it with when concrete. Yeah. Good.
So basically, what it does here, if we omit some of the details, it calls this operation type thing. This is a built-in keyword, basically, and it passes the binary expression itself and the left and the right types that are these two variables here, right? They have been calculated. Basically, it waits until the left type is calculated and then assigns it to this variable left. And so we call this operation type thingy with the object whose type we want to calculate and the left and right types themselves. And this then magically calculates the result type of our operation, and then we assign it, right? We just say the type of the binary expression is whatever has been calculated by this magic.
Yeah.
Okay? So let's try to understand the magic, because obviously it's not magic. So here there is this binary operations container, overloaded operations container called binary arithmetic operations. If we take a look at that, So here we basically specify the typing rules. And now the trick is that these typing rules are specified in a way so that they can be overridden. You can add additional typing rules in other languages, and that makes it very interesting, because language extensions must be able to override typing rules defined in the base language. Like if we defined money, right, as we did it in this other example, then we have to define what happens if we add a money and another money. And so you do that by just creating another one of these things. So let's look at one of these guys. Basically what it says, that if we work with a diff, plus, minus, or multi expression, and the left and right arguments are primitive types, then this rule here is applicable. And then it basically calculates the supertype of the left and right argument. It uses a helper function here. So the point is, if you want to calculate the type of, if you add a money literal and a number, then you would just write another one of these thingies here, of these overloaded operation rules, and you would say left side is money, left side is number, and then you just calculate what the result is, probably a money, or maybe it's not possible. We recommend you take a look at the money screencast, where we showed how that works for that.
Yeah, that was an example of how to extend this, how to build it for your own language.
Right. Okay, and the last thing I wanted to show is the return statement, because of course the return statement has to be compatible, or the return statement's expression has to be compatible with whatever the function has, or returns, the function in which the return statement is. So how does that work? Well, that's probably easy now. We can go to the typing rule again, and we basically oops, sorry, running out of space here. we basically say that there's some special handling for closures, which we don't want to look at now. So basically what happens is that the type of the whole return guy is the type of its expression. That's the usual, just infer the type of the whole thing.
Yeah, you infer the type of the return. All right, good.
Yeah, and then we want to make sure that the type of the return is the same or subtype of, and then we go from the return up the tree until we find something that's function-like, and that is an interface that is the supertype, in this case here, of functions and operations and methods and all these other things. So we basically go up the tree until we find the function, we grab its type, and then we make sure that the type of that guy is a supertype or the same as the type of the return expression here.
Okay, cool.
Yeah. So
well, that was, I think, how would you rate this on kind of the complexity scale of type systems? Now, what we've seen so far.
High.
So this is probably, this is something that you typically don't need.
Yes.
In your languages, people rarely get to a stage where they would need such complex type rules, would they?
I agree. I mean, this is a set of typing rules for a real programming language. I mean, we have to handle arrays, we have to handle pointers in C, right? So there's a lot of interesting stuff going on. We have to deal with multiple parallel hierarchies. For example, an int 8 is a subtype of int 16, and it's also a subtype of float. So getting that right is really quite involved. On the other hand, if you look at Java with all its generics, that's way more complicated, and I wouldn't be able to explain base languages type system, right? I couldn't do that. And so I agree that it's probably more complicated than in your kind of hello world DSL. But on the other hand, if you write language extensions for C in this case, or for base language, then sometimes you are confronted with this kind of complexity, and you have to sometimes understand, and it's not always easy.
So you have to go down to these rules to sometimes, if you're extending this language, you sometimes need to check the rules and understand them.
Well, you have to make your own thingies kind of fit in with the rest of the system. And of course, I mean, if you simply add a new kind of simple thingy, as we did with money literals, then I mean, we recommend you look at the screencast. It's easy. But depending on the sophisticatedness of your language extension, you may be confronted with the type system. I mean, the point is, what's the alternative? I mean, if you look at other tools which don't have any support for type system specification at all, you have to write all that programmatically in Java code. That's not any better.
Right. Of course.
Type systems are complex, and at least for non-trivial languages, and that's what you have to master if you want to build non-trivial languages. And MPS does a superb job in supporting that with this type system DSL.
Yeah,
But
well, you're right. Now, and certainly, having the implemented type system, you get a lot of benefits, right? It's like you don't do it just for for the sake of it. You do it because then the type system will be able to give you hints and help you write correct code and prevent you from making mistakes.
In other words, what you're saying is that if you're just learning MPS, implement a dynamically typed language so you don't have to do any typing rules.
Right, yeah, that's an alternative. Just apply types later when you feel fit, when you feel that you miss them.
Yeah.
That's a good advice.
One last thing, and that is that because the type system works the way it does, it can automatically handle inference. So let me just do one last demo here, right? So we create a function that returns an int, and it's called do something. It takes another int as an argument, and it takes a function as its second argument, which takes an int as its argument and returns yet another int. Right, so this is a higher order function which takes another function as its argument and an integer here. And so we return function of arg. Right? So we apply the function which we pass to the argument which we also pass.
Right. So you can return an integer. Right,
yeah.
Good.
So now let's write a little function that is compatible with that. It's called times 2, which takes an int and returns an int and returns 2 times, we should give this a name, 2 times a, right? And now we can call the do something function, passing in 12 and passing in a reference to times 2, right? So we've called the do something function with the number 12 as the first argument, and with a reference to that function which is compatible as the second argument. But we can also call do something 12 with a closure. Okay? So that's an extension that we've added to C. Now,
that's a very compact syntax, huh?
Yeah.
No types.
No, and that's what. Thanks for mentioning that. It's almost like we practiced. We didn't specify the type of X, but if we go here, it knows that it is to be int. So there is a type inference rule that inferences the type of the arguments from that function type signature.
Wow, cool, man.
And that is literally, I'm not going to show how it's, well, I can show it, but it's basically literally one line of code or 2 lines of code that I had to write. It's really simple. Probably find it here. It's like, okay, it's a little bit more. But it's not a lot. And so because MPS type systems works the way it works, you get type inference almost for free because the engine performs type inference anyway. So if you want to write languages that have type inference, like in this case, this is very simple with the type inference engine or the type system engine from MPS. So that's one of the benefits you get from that system. But okay.
Awesome. I think that was a nice demo to kind of wrap up this screencast.
Okay.
Thank you, Markus, for showing all this to us.
It was a pleasure. I hope it recorded.
Yeah, hopefully. And thank you everybody for listening and for watching us, and stay tuned for more.
Okay.
Goodbye.
Bye.